Yes.
But I think that to realize a hydrostatic phase, the planet-similar accretion is necessary. But when the planet mass reaches isolation mass, there is no planet-similar.
When the planet reaches the isolation mass, there's no solids anymore in the local feeding zone, you mean? Yes, okay, these are okay, but no big, yes, but this is, okay, you're right in principle, yes, if you have, that depends a lot on the interaction, let's say, how much material you can bring into the vicinity of the planet. I mean, this is a very good argument, I think, yeah. In the inner parts of the terrestrial planets there's always very little gas available here, so you clean out the material there, and there's no new material coming back. But in the outer parts also, you have also larger reservoir of material there, of course, and then materials can be fed in, let's say, in the later phases also through drag with the gas. You can get more material there. But in principle, I think it's a very good point that you have, let's say, there's an isolation mass definition there, and you nevertheless continue accreting material there. Yeah, but you can see the core mass is constant for a very long time. You can see this in time. So you reach the core mass, and then you have a very flat region there. Yes, and this flat region, this is basically the region where there is not much material anymore available. If you saw the curve, yes? So this agrees with the argument of an isolation mass here, okay? This one here. So here reach the isolation, the core mass basically, and then you can have a very constant mass here for a long time, okay? Yes? Okay. Yes, okay. The question is, given Jupiter's mass as we observe it now, if it can be explained by this gap formation process, how do we get these larger masses for the exosolar planets? So this is a very good point, which I will answer tomorrow. I hope so, at least, yes. This is not the final story here. You can still accrete mass here from these, where was the picture here? You can still accrete mass through these streams of gas which enter here the Roche-Low basically. This is still possible if you have a gap. Okay? The gap is not completely empty. This is the whole point. Initially it was thought, okay, you can open up the gap, you have the torques there, you can open up the gap, but nevertheless material can still be accreted into this system here. It's very similar to what Phil said yesterday, in fact, with the circumbinary disks. We have a binary there, which is a very massive planet, basically. So there would be a very, very deep gap, but nevertheless, the binary can still accrete material from the disk there through these so-called, let's call it, streamers, in quotes. This is very loosely speaking, okay? Yeah, spiral arms which extend to the object, then you can go into the inner parts and be accreted. Yes.
How significant is the energy generated by elements like 26 aluminum?
I think in particular that element, what is the half-life of aluminum here? It can be taken into a...
1 megayear.
Yeah, so it's if it's still there, you're talking about a few megayears here possibly, yes. If it's still there, it can be taken into account. It's taken into account in the models. Sorry? Yes, I think at that time is already more. But if it were there, it could easily be taken into account in the models. You would just add an additional luminosity from the core. Yeah, so this could be done, I think. But you have other radioactivities, yeah? Other elements still available there, which may give more.
I think that concludes our 5 minutes of questions then.
Yeah.